I'm always a little bit daunted when I have to talk to a kind of general audience about my work. If I paraphrase my mother, who continually asks me, you know, what is it that you do? It's kind of difficult, and you know, I often tell her that one of the great kind of applications of theoretical physics is as a sedative, you know, when I talk to, or a contraceptive, depending on who you're talking to. But anyway, but listen, on a serious note, I think it's really good that we're discussing the interface between quantum physics and the arts. Thinking, you know, on my feet, you know, if I think about how a theoretical physicist works, it's ultimately a creative endeavor. Just like any other form of art, for example, you could painting, sculpture, music, whatever. These are creative endeavors which are trying to, you know, use some medium to interpret something abstract. And that's not really any different to working in theoretical physics, except you use the tools of mathematics. And most importantly, and what's, I guess, sets theoretical physics kind of maybe apart from arts and other creative endeavors, is that it's actually much more constrained in what you do, because you're constrained by physical laws, which are ultimately testable by experimentalists. Okay, so that's really the way I would see. They're creative endeavors, but in some sense, being a scientist is a lot more constrained. You're not constrained as much to interpret something in the arts, and I think that's wonderful, and that can actually help physicists also come up with ideas which are perhaps less constrained. So, you know, the topic is quantum mechanics, and maybe I just ask for a show of hands in the audience. I mean, who knows something about quantum mechanics? Okay, that's quite good. That's quite good. So actually, you know, coming back to this idea of constraints, you know, how quantum mechanics has been around for a long time, more than 100 years now. And actually it was precisely, you know, a constraint or an anomaly which led to its discovery, which was a complete fluke, which is often the way in which science develops. So you have some phenomena. In the case of quantum mechanics, it was a particular problem where physicists were interested in the spectrum being emitted from a very hot object, and it simply wasn't fitting their equations. They had it wrong. The physics that they knew at the time, at the early part of the 20th century, people thought that they understood everything. But then what happens in physics is you really get a paradigm shift when you get some data you can't interpret with your theory. So actually, it was really a fluke. Max Planck was the guy, he was a German physicist actually, and to quote him, in an act of desperation, he let the energy be emitted in fundamental units of a constant, which now bears his name, Planck's constant, okay? And after that, you know, the whole theory was formalized over the 20 years that preceded that initial discovery. So please stay with me. I mean, I know it's a little bit boring, but I want to set the scene. So, you know, after that initial fluke, our discovery, people started to put together the pieces of this jigsaw. So to give you an analogy of how, you know, you construct a theory, it's a bit like, I think it was Feynman who used the analogy, he's a famous physicist, American physicist, is that you're sitting down and you're looking at two people playing chess, but you have no idea what chess is, but you just look at the moves they make, okay? And then you look and you stare at them playing chess, and you think, okay, now I understand that a castle moves this way, a horse moves this way, or whatever. And then all of a sudden, a rare thing occurs, like a rule, and you go, oh my God, I didn't really understand that. So that's what happened for about 20 years after the original sort of fluke. And then a theory was formalized by people like Erwin Schrödinger, who spent a long time in Dublin, actually was headhunted by De Valera. So De Valera himself was actually from a mathematical physics background, and he formulated an institute called the Dublin Institute of Advanced Studies, which was basically set up to host Schrödinger. It was a rather controversial character. I don't know if you've read the recent Irish Times articles or whatever, but we won't get into that. But you know, he was one of the founding fathers of the theory. And Schrödinger understood very well, if you took the logical consequences of this theory called quantum mechanics, okay, to their sort of ultimate conclusion, it gave you things which are quite frankly scandalous, okay? Let me explain that. So quantum mechanics is a revision of physics to really incorporate this fluke that Planck first discovered. And it's something which is very, very uncomfortable, because in the usual physics, so in the type of physics that you learn in school, you always remember doing these super boring calculations. A ball rolls down an inclined plane at an angle of 30, this stuff. So like the assumption that there is a ball and there is a point-like particle that you can abstract to in quantum mechanics goes out the window, because quantum mechanics tells us that you can only really talk about the probabilities or potentialities for things to occur. So that's actually a radical revision in the way we do physics. If you talk, if you go to a high school physics, person, they will say within the realm of what they've kind of known, like if you give them enough data, initial conditions, and enough sort of computational power, you can basically predict the future outcomes and physical observables with an unprecedented kind of accuracy. But in quantum mechanics tells us, no, there's no reality, okay? Actually, it's only emerging as a consequence of your measurements, and the outcomes of your measurements are intrinsically probabilistic. What do I mean by that? I mean that you may be uncertain today about the population of Dublin, right? But the population exists, the number exists on a given moment in time. Quantum mechanics tells us that things, they have no meaning until you measure them, and when you measure them, you have an outcome which is probabilistic. So you get some probability.
I said I would interrupt as soon as you started saying controversial things, and if you hit that point already. Are you happy for an interruption?
I'm absolutely happy.
Okay, because you were speaking sometimes as if we'd sort of established the formalism of quantum mechanics, and we sort of knew what it was saying, it has a history, and we've now started to get sort of beyond that. But interestingly, you're already touching on what is considered sort of foundational or even philosophical issues about, is it the case that the world is a certain way before we measure it, or is it like our measurement makes the world a certain way? And for a long time, people were happy with, I think, the interpretation you're sort of suggesting here, where, we have a very precise mathematical equation, but we find out that the world is probabilistic and that our observations of the world are partly what makes the world a certain way. But, at the same time, there was kind of a counter trend right from the beginning with even people like Schrödinger saying, well, actually, maybe that's not what's going on here. The world is always a certain way, and we might be ignorant of the way it is, but it's in fact deterministic all the way through. The probabilities involved, there are probabilities, but if we knew everything in perfect detail, we would still know what was going to happen next. I'm not sure if you want to say more to that beyond sort of just, that is a point of controversy.
I think it's great when you see a philosopher getting, irate at these, because I share actually Alison's concern. As a side remark, we were just discussing with Alison before we came down here, we were actually discussing asymmetry in the physical laws in the Dawson Lounge just before the lockdown. So I see this as a continuation of this argument or discussion. But yeah, I guess what you're alluding to there is that, maybe the way that I'm explaining things, and I think that's fair, is too conventional or like orthodox. Like there are different ways of interpreting the emergence of probabilities within the theory, okay? That's something that I won't answer tonight and people will still be talking about. And, 100 years ago, nothing much has changed, but a couple of things have, and I should really kind of, I think, make a comment on that as well, right? So what has changed, actually, in 100 years? So when they formulated the theory, Schrödinger, for example, he actually coined the word entanglement, and I would be surprised if it wasn't in Dublin when he thought of that word, but we can see. But what does that mean? It means if you now consider more than one quantum system, so have in mind, what are quantum systems? Anything in my mind, but typically the things that obey quantum mechanics, strictly speaking, are single quantum particles like atoms, like electrons, or like single particles of light, which are called photons. And what is entanglement is the next question. I don't know how many people here have heard of Schrodinger's cat paradox, okay? So one of the weird, scandalous sort of consequences of the theory of quantum mechanics is that particles, before they're measured, okay, they can actually be simultaneously in two places at the same time, okay? So for example, you know, really the way to think about it is that, you know, if I manage to put a particle, an atom, or a photon into a superposition, we say, then really it is in both places at the same time, and then the moment you ask where it is, it collapses into one or the other place with some probability, okay? That's superposition. And entanglement is when you get two quantum systems that talk to each other, okay? And they may then leave each other's presence. So they interact with each other, they fly apart, fly across the universe, and the absolutely mind-blowing thing that quantum mechanics predicts is that measurements on one particle, which bring that particle's state into existence, automatically determine the outcomes of the other particle in a distant spatial location. This is what we mean by non-locality. So around 1930 or so, Einstein and others, they picked up on this issue. They wrote a famous paper that was actually on the front page of the New York Times, where they actually used this as an example to say that quantum mechanics is actually not complete and there must exist some higher order explanation for this, okay? So many people talked about it at the time, but again, to quote Schrödinger, I mean, he thought that, look, yeah, sure, it'll be superseded by another theory at some point, but actually to think about these anomalies and get single quantum particles, and I'm quoting him, it's about as probable as raising an Ichthyosaurus in the zoo. You know, there's no chance that you'd ever be able to isolate a quantum system in the 1930s, and that was true. Fast forward, you know, 60 years or so, and I think this is really what's changed, and that's what's exciting, and that's why, you know, people are interested, is that we not only can isolate single quantum particles and interrogate them, perform measurements. This year, the Nobel Prize for Physics was actually given out for the experimental demonstration of entanglement, okay? So, and that was that was due to theoretical prediction of a man called John Bell that was mentioned in the introduction. He's unfortunately not alive today, but were he alive, we would have another Nobel laureate in science on this island, no doubt, and probably earlier it would have been given out for that. And so again, this is really weird. Like, the fact that things can be in multiple places at the one time, the fact that measurements in this room can instantaneously affect the outcomes of measurements in another place in the world, or, you know, this non-local feature of the theory, it seems absurd. And what was amazing about John Bell's work, which was a hobby for him, because he was not a quantum physicist, he worked in CERN, okay, he was a high-energy physicist, he used to study quantum foundations at the weekend, was that he was a follower of Einstein. He believed the same as Einstein. You know, this is absurd. How can I actually demonstrate, you know, that this is, and he wrote down basically a theorem which, if obeyed, shows you that some higher order theory exists, okay? And this theorem has now been violated in labs all over the world routinely. And just to finish up on that before Alison comes in, because I know philosophers are super interested in this, what is also interesting from an engineering perspective, it's precisely this feature which is exploited now in the emerging technologies in order for us to perform certain tasks faster. For example, you know, we can construct algorithms using the laws of quantum mechanics. If we can really isolate and control many quantum degrees of freedom, this is quantum computing, which, if successful, would compromise the entire encryption system in emails. So for example, if you send an email, its safety relies on the fact that it's multiplying two very large numbers together and asking you to find the factors, okay? But if we could construct a quantum computer, we could actually solve this hard mathematical problem very quickly. It's a problem that current computers can't solve. So that's why there's so much money being pumped in, 15 billion by the Chinese government, further 10 billion by the US, 7 billion by the EU. This has happened over the last, you know, 5 to 10 years as we approach a technological era whereby we can manipulate quantum systems and explore consequences, the weird consequences of measurement, entanglement, and superposition.
Cool. for what it's worth, I'm very happy where you ended up with entanglement, superposition, and non-locality as kind of the major markers of quantum mechanical systems and what is being exploited in these new technologies. I guess from a philosophical point of view, what's really interesting about the state of play here, we have these emerging technologies, we have a very nice formalism, and we have no clue what it means about what the world we're living in is actually like. So I understand, usually when we're taught quantum mechanics in physics, we kind of skate over what's known sometimes as the measurement problem or a problem of interpretation, as if it's some kind of like optional extra, which I think is quite funny. But even if you ask, a quantum computing system, what is actually going on here? Are these particles in one state or another, or are they in both at once? Is it determined which way they'll go? These are some of the questions which philosophers like to care about under the banner of this problem. And just to give you the flavor of what the solutions look like, we have a kind of big three available at the moment. One, maybe the most famous one, is called the many worlds interpretation, which tells us that, well, actually, every time you do a measurement, all the results happen. There's no probabilities in play. You can measure something one way and the particle it's entangled with will go the other way, but also the opposite result will happen. And that every time we're doing measurements, all these possibilities are always happening. What's kind of crazy here is that the world doesn't look that way to us. No one wanders around looking at people splitting or world splitting. And so there's a kind of built-in ignorance, if that's our picture of the world, that kind of we're stuck in kind of one area of what's called the wave function, and we can't see what's going on the other ones. But this idea that we're doing measurements with probabilities, that's kind of an illusion on this model. There's another nice model which kind of messes around with the formalism, and so physicists don't really like it. But this is the only one in which the dynamics is actually probabilistic, where there's actually probabilities of it going one way or another. And that's to add in some kind of mechanism where the world is kind of uncertain and then gets kind of collapsed to certainty at various moments when you make measurements, typically involving, big things. And the third one, and the one that I would say John Bell was kind of more in the direction of, is one where, the world always has a very determinate state and always determined exactly which way it will go. It's just that there's all these kind of non-local effects, so that the particles are behaving as if they're responding to other things that are far away from themselves in a kind of weirdly indeterministic looking way. And so again, it's one of these other interpretations where the way the world looks to us is like horribly misleading, because actually quantum mechanics would be just as deterministic as classical mechanics was in Newton's time, but it would be kind of hidden from us because of our uncertainty about where we are in that system. And what I love about this is, to me, these are like the huge questions to ask, and nevertheless, we don't need to actually answer them in order to go on and do plenty more stuff with quantum mechanics, which I find it fascinating to be in that state.
Absolutely. I dedicated most of my life to studying it, so I'm fully on board. And if you understood everything, it wouldn't really be any fun. Actually, Alison touched on a very interesting point that maybe, given that we have this fancy theory, the other thing I should point out is that it's not just a theory. Really, we can go to a laboratory which produce very, very, to good approximation, an isolated quantum system, and we can perform experiments which will actually vindicate, the predictions of quantum mechanics with, I would say, an unprecedented accuracy, like unprecedented in the sense of, the type of accuracy that you get in other areas of science, right? So really, it's quite impressive what people can do now. And Alison touched on a very interesting thing, which is, one thing which really excites me as a physicist is we experience the world as human beings in a very classical way. But, that's because we're continually making measurements. In some sense, we are only a product of the measurements we're making on our surroundings, right? Like if you didn't have any sense at all and you made no measurements, there would not be an existence in my mind, right? But this is something, again, that maybe I'm like, bells are raising for the philosophers, but I don't know. I always found it interesting that, I said upstairs to people that I thought that one of the problems that we have as scientists is that we learn quantum mechanics too late. You know, we learn it when we go to university. It's seen as highly specialized. In my mind, it's actually a very easy theory to learn relative to other theories from a mathematical perspective. It's difficult conceptually. I would argue that you could teach it to high school kids and they might actually be better than it than us old guys, right? Because already, I think, as you age, you lose the ability to really think abstractly. I think kids are much better than that. They grasp concepts much quicker. So we're taught classically physics for like 10 years. And then we go to university, we learn quantum mechanics, and we find it so hard to get our head around. But if you're taught from the start, maybe it's not so hard to think that way, you know? That's maybe...
It's a lovely point to end on, you know. Yeah. Hope for the future. It might just be easier for the next generation having been trained as young people.
And yeah, I mean, I think, you know, in the end, really, you know, it's difficult conceptually. It's nothing to be afraid of. It is something that people will hear more and more about as, you know, society moves into an era where quantum effects are being exploited in technologies, right? So technology isn't a dirty word, you know, for a theoretical physicist or a philosopher. I mean, technology can also give us very good ideas. It can inspire us in fundamental science. It can inspire our art and it can inspire our music. And, you know, it in some sense is a whole new way of thinking about the world around us, right? So I would say that's kind of why I would see this interface with the arts being extremely important.